Hello everybody and welcome to Handmade, here the show where we code a complete game live on stream. Yesterday we covered how to look at camera transitions. We introduced the concept of cubic and how to design one and parameterize it in a way that allowed you to do a nice ease curve. And we wrote some code for that. Which we employed as a test, and in order to do that, we just simplified the way the camera was working really quickly as something that allows us to sort of do transitions between rooms using the function that we designed, right? And so what you can see here is that I can do this transition when I move from room to room, there's no particular tuning to it currently, but we did implement the function we wanted, and now we can tweak that cubic as necessary, right? But we have another problem that we need to solve, and that's what I said at the end of last stream we would do today, and that is we want the ability to have the camera track a moving target. So if all we wanted to do was move from room to room, which is what we're doing now, we would kind of be done there because you could actually just leave it implemented the way I implemented it, right? And you might have some issues where when you hop from room to room, you get some kind of maybe a little bit, like you can see if I hop back and forth, maybe that's not as pleasant of a motion, but even that's really not that bad. So, if we didn't need to track a moving target, you could call this done. And all you would really want to do is maybe tweak the function to get the exact amount of easing that you wanted, or, play around with that curve until it was something that felt like the curve that you wanted to feel, right? But we're not quite at the point where we can call it done because we do want to track a moving target. And so when the player hops up and down this corridor, for example, we want it to follow them vertically. And so this puts us in an awkward position because the only technique that we really developed yesterday for using that cubic required us to have a known start time and a known end time for the interpolation. And if the target's moving, we no longer really know that, okay? So let's talk a little bit about what I mean by that. That is, if I can find the pen, and by that I mean Marine Le Pen from France. Let's see here. I guess I don't know if anyone's ever tried to draw with her on a tablet, but there you go. All right, so let's go ahead and talk about this. Moving camera target. So if you look at, for lack of a better term, the behavior of the camera that we wanted, what we were saying is that we want the camera to move, from here to here, and in that process, we wanted it to follow a speed curve, if you will, right? If this is the speed, we wanted it to follow a speed curve that sort of looks, something like this, right? In other words, we want the rate at which the camera is moving to look something like this. So as a result, we defined a function that had that kind of a look to it. I mean, I guess you shouldn't say that. The speed of ours is kind of more like that, right? But that's what we wanted. Low, high, low. And so this is a parabola, right? And when we look at the position, that's when we get the cubic that we designed, okay? So if you integrate this up, you get something like this: slow start, fast middle, slow end, right? And that's exactly what we would expect here if this is our speed and this is time. So if we want our speed to look like this, and more importantly, I suppose you could say, if we wanted to write any given function for our speed, meaning we want the speed to be proportional to where we are along the motion from here to here, right? um, then what we could think about is maybe what we're really saying is we don't care so much about the cubic, right? The cubic is a way of getting the position by having previously integrated this parabola, right? Because we're doing, you know, at3 plus bt squared plus ct, right? This is our equation for our position, right? So like that's, you know, that's pt. So if we take the derivative of it, right, if we say what's the speed of this equation, then we're gonna get we're gonna get a second order equation, right? If you take the derivative of a third degree polynomial, you get a second degree one, right? So you get 3at squared plus 2bt plus c as our speed, right? And so really what we were talking about, like we didn't care about this, really. What we were trying to say is this is what we want our speed curve to look like. Because remember, it's the ease in, ease out that we were looking for. We don't really care that much about the position other than we need to get it as an answer. But other than the fact that it goes from A to B, it was really the speed that we were talking about that we wanted to articulate to the math. And all we really used the cubic for was to get the position out of that. Right? So, the next question is, well, all right, what can we do then to make our interpolation work in some way that doesn't have a fixed start and end? Because what we have to know, right, is that at the start, right, at t equals 0, right, we want our speed to be 0. You know what I mean? And we want it to pick up over time so that when we're about halfway, you know, we want our speed to be, you know, 1, let's say, where I don't really mean the literal value 1, but I mean some value. I mean, we could say max, right? We want our speed to be the maximum speed, whatever we decide that to be. And then we're at t equals 1, we want it to be 0 again, right? That's what we wanted. The problem is this and this are now not really known. In a sense, we can remember what t equals 0 was, because we know anytime the camera stops moving. So if the camera stops moving completely, we could know that. We could detect that the velocity of the camera had diminished below some threshold and say, we are now at rest. And then we could remember when we start accelerating out of that rest and call that t equals 0, and then we could track that t over time as much as we wanted, right? But if we don't know when t equals 1 will be, we still can't construct the curve. And why might we not know what t equals 1 is? Well, let's suppose that the camera is at rest. And then, so we basically have, in our parlance, we have a target, and we have the camera, and it's moving to the target. When it arrives at the target, right, maybe I'll do it this way. So when the camera arrives, so the target and the camera are in sync, right, then we can sort of say the camera is at rest, and this is t equals 0 and will remain t equals 0, right? There's no speed, it's just at rest. Now the user hops from one room to another, and let's say this is focusing on, like, the center of the room. The user hops from one room to another, and we're right back in the situation that we were up here. Oops, backwards. We're right back in the situation that we were up here, where we have the camera here and the target here, and now we know that this would be t equals 0 and this would be t equals 1, and we want that smooth curve from one to the other, right? And the crucial thing to remember here is, in a sense, we want potentially that, we don't know exactly what we want to require here, but we may actually also want to say, look, we want room transitions to be nice and snappy, so we want them to always take half a second or 1 second or something. Like, we may want room transitions I don't care if you're going from a small room to a big room or from down a long corridor. We want those room transitions to be fast because I don't want the player to, have to sit around waiting to see what's in the next room. They're supposed to get it, it's supposed to be a nice, pleasant visual effect, but that happens snappy, right? So pleasing movement, but fast. So we don't really know. We may want this t equals 1 to just be assumed to be here, or we may want to say, well, look, maybe we want to take how far away it is and say that we don't really want our function to ever produce a velocity higher than a certain amount. So we want our curve to start at 0, go to a maximum velocity, remain at the maximum velocity, and then end, right? So in other words, if we want our room transitions to happen in constant time, meaning like, 1 second always or something like that, then our thing can look like this. Because we can always make a parabola that gets us there on time, and the height, this right here, will just change, right? So sometimes the parabola will look like that, sometimes the parabola will look like that, you know what I mean? In terms of what our actual speed ends up being when measured in the world. But we could always make it there in constant time just by making the speed bigger. And the way we're doing that right now is we always use the same parabola, but we just blend between points that are further away, right? So we don't actually use the parabola as speed. We use the parabola as a normalized speed, and then we stretch it out over a line, which is also a totally valid way to do it, right? But either way, point being, that always gets us there the same amount of time. So in the actual game, if I'm going from here to here, which is a smaller movement, right, the camera can move at a slower speed than from here to here, where it has to move faster, right? It has to move much faster there in order to get, because the points are further apart. But we could instead decide, and this is an artistic decision, right, that affects the math, we could instead decide that we want a curve that looks more like this, right? So there's a start and end to the parabola, but in the middle there's just a long linear region. So there's a linear region, and there's like an acceleration and a deceleration, right? And so this parabola is really split in two, and there's an intermediate area that's just a constant speed, which is the maximum speed. So it goes up to its maximum speed, stays there, and then comes down from its maximum speed when it's done. Okay? I can't say that I really have a strong opinion about what should be happening in that case. There's a couple different ways we could do this. Given all of those things, there is sort of another thing we could do, which is just making the player's location always be the target, and then if t equals 0, then you just move the target. So I don't know. I just wanted to kind of get all of that out there and just talk about what the possibilities are, because I don't know exactly what we want in this particular case. I don't have an editor open, so here we go. So I guess it depends. It really depends on what we want to do. But in terms of the way our camera is at the immediate moment, if we take a look here and we just say update camera for entity movement, if we wanted to say that the way that it works is it always takes a constant amount of time to switch from one room to another, in which case we have the from P to P construction, and we leave it this way, and then we can make whatever function we want here for their interpolation. If we did say that, then one interesting aspect of that, one interesting thing that comes from that, is the fact that the camera itself could then just be locked to the user in all other cases, right? So, yeah, like effectively we would say something like, if the target and the camera are close enough to each other and t equals 1, then we just set them equal to each other. Otherwise, we update the target. I know this sounds a little bit weird, but that's basically what we would be doing there. So, yeah. Let me see how, if I was going to, just to give some explanation of that. So, in here, where we set this in room and not is equal to, right? So what this was doing is this was preventing us from ever setting a new camera, right? So we never update the camera when we move rooms, except for that first time. Once you're inside the room, you'll never update the camera again. That means that things like our tracking the player scrolling, we would never even hit this case, right? If instead we said, well, you know, maybe what we really wanted to do was always update the target, but only update the from and, only update the t interpolation and the from p when we actually do a room change, right? So only do that interpolation at that point. And if we do something like that, then, you know, what you would see is we still have constant time room transition, but once you get into a room that scrolls, you're just locked to where the player is, right? You see that? Now, the problem with that, to a certain extent, is locking to the player, you can see there's a certain amount of smoothing that isn't happening there. So, you know, I don't know to what extent we would probably want to smooth that out, because hopping is kind of jarring, right? You can kind of see it being fairly jarring there. And I'm not really sure why the Y is being changed there instead of the Z. That's probably old, like, historical reasons, so we can probably fix that part. But you can kind of see that we would want to smooth it out. But other than smoothing it out, it's not immediately clear we couldn't just use that, right? Because it does track the player just fine. And then our interpolation, you know, so really what we have, for the most part, is a problem with smoothing out the player's motion, not a problem with what the camera would do in this case. Right? So if we imagined doing something a little bit different here, tracking the cameras in room would not really be necessary either, right? So what we could do here is say, look, we don't care about any of this. All we really need to know is if the from P and the P are like really far apart. You know what I mean? I'm sorry, if the current location of the camera and the new location of the camera are really far apart, and t is less than 1, I'm sorry, t equals 1. So if we're not interpolating the camera, right? So this means interpolation is over. And the difference between these two vectors, the length, happens to be larger than whatever our maximum is. So like distance between squared, something like that, from target P, like that. So if the distance is greater than, you know, some amount that we consider to be a large movement, you know, like a meter, then we restart our interpolation. Otherwise, we just snap. You know what I mean? Then we don't really need the in-room. I don't know if we've got a distance between. It don't look like it. So we can just say length squared of the vector in between. So if the amount we wanted to move was greater than some max distance, so like max distance per frame, you know, is something, and it's probably less than that. If we were going to move more than the maximum distance per frame, then what we do is we start an interpolation. Otherwise, we do nothing. That would mean that we don't really have to set anymore the in-room, and that goes away. So then we just have t interpolation and the target from construction, right? I need to make sure we set the from, though. Yes, we did. Okay. So that's all fine, I think. All looks good to me. So let's take a look at what happens there. You can see us now. It looks like we're getting a weird glitch there. So I think our from p is not quite right there. Yeah, so the problem is that's going to get re-encoded. So we don't really want to do that. We want that to be re-encoded here, like so. So we really want this. Right? We don't ever want to be copying in the unmapped space, in the, you know, in world space. We want to be mapping in like simulation space. So now we pretty much just would work no matter what we did. We don't need to know about rooms or anything. The camera just works. And so now we're just down to wanting a more pleasant effect when the character is hopping, because we don't really want to account for all that motion there. Ooh, what happened there? Something weird happened there. All right, so there's something busted about that. Let me take a look at what's going on here. I guess that may have been us hitting the max distance per frame. No, I'm not sure what that was. Target P. Target P is always set. So that really shouldn't be an issue. And it's always mapped into the region and out of. So that all looks pretty good. Did I mess up anything else here? Here's the T update. I'm gonna put that down here actually. These are still kind of doing their own thing, which is fine. They could actually be rewritten this way as well, which I should do because, you know, we can just lerp them in addition. So we actually don't need to do this anymore on them. But I'm not sure why they're getting that weirdness there where I was seeing, yeah, I don't know why we were getting that hiccup, and I'd like to take a look more closely at that. What I do want to do here though is I would like to make these be something that goes off of the Bezier magic, so they would interpolate basically the same way that they would just interpolate the same way everything else interpolates, right? Because once we've made our blend here, so I think this is our, you know, blend factor. Once we've computed what that blend factor is, I would like to use it for everything. So, you know, this would also be a lerp, where we would take the expected focus min z and the expected focus max z, and we'd blend between those. And that way it's also stable per frame and doesn't have a weird, like, doesn't have like a weird dependency. And I just want to take that out of the mix so that we're not getting like weird results due to that or something. If that makes sense. All right, so yeah, like most of the things look okay here. It's just not that one particular thing. And so I'm not sure how we want to deal with that. And you can kind of see it actually looks like we get like a positional hiccup even. We definitely get some hiccups on the blend, I think. Yeah, like that was an actual positional hiccup. So how are we getting a positional hiccup there? What's going on? We do map everything back in, right? Everything always, the from P and from P, target P is always mapped, just period, right? Target P is always mapped, and the target expected focuses are always kept from the destination. And you know, I wonder if that should just be based on the camera directly. I don't know. That's hard to say. I do wonder if these maybe should be measured from the camera directly after we interpolate it. So that's a little hard to say. Like, I don't know how much blending we really want on those one way or the other. But, so something weird is happening here where if the camera interpolation needs to hop back, something bad happens. I'm not entirely certain why. Because if you think of what would happen here, maybe let me just walk through it. In the case where we set the interpolation here to 0, we're going to set the from value to be the same as the p value. And the t interpolation will be set to 0, so this whole thing will basically just mean that we're at the from p, which means p will remain completely unchanged. And so you shouldn't get a hiccup there. So I'm trying to figure out, maybe the way you get a hiccup, though, is by changing the target P to discontinuously. So, yeah, I guess what you could say is if the target P was changing too much, it would also need to do this. You know what I mean? Because you could get a discontinuity if you haven't finished an interpolation and the target P has changed too much, then in a sense you need to like restart the interpolation. You know what I mean? And so that's like kind of a rude awakening there. And maybe sort of motivates the thing that I was talking about before, where it's like we need a thing that allows you to have a moving target, because occasionally you do. So I don't know. The way we would do that is, I think, all we would say is restart interpolation is a value that we can trigger. And then when we're here, we can just say, look, if we move the target too much, and I guess, you know, another way to do it would be to say, looking at this, right, if we make the target P be something that comes out here, so the target P in this case gets pulled out early. And in fact, I guess all of these can be pulled out early. So we would say, grab all of our stuff. If we want to update the target P, we can update the target P, right? But we would want to say something like new target P, right? So in here, we would say like, okay, target P. So when we get our new target P, and then of course down here, we would want to map everybody back into the chunk space for storage. When we get our new target P, we now know when we get down here how far each of these things moved. So we could say, yeah, if the amount that you wanted to move was greater than this, you would restart the interpolation. But also, if the target P itself moved enough, you would want to restart the interpolation. So it doesn't really matter how close they are. And we probably could have solved that by just reducing this value, but it just seems, sensible there. So if you move the target P or you move the new target P, either way, and then after that, we set it up. So if either of these moved an appreciable amount, then we swap it over. And if we're not in a room, if we are in some kind of error condition, then we just don't update it, right? We just use whatever the last one was. Oops, I messed something up there. So yeah, like we get all this stuff here. Camera Simulation Center. Should probably be handled outside as well, but we'll leave it there. So setting the new target P, I missed one. Looks like you can see the target P down there. I don't know what I did there accidentally when I was replacing that. I just didn't go far enough, right? So that's the problem. But yeah. So let's see, if we are going around here and now we're still glitching out. I'm really not sure what that's from. I'm not sure where else we get that. I have to think of a good way to debug that because I'm not sure how to look at something that happens across that frame. We'd have to figure out what was going on especially there. Because this should never do it, right? Because from P just gets reset to P, which would not move the camera. If interpolation is set to 0, because you should come through with P equal to from P in that case, because blend is 0. Right? I mean, in theory anyway. Like, I don't see why we would get that discontinuous jump. I'm curious if it has to do with that resetting or not. Since that's the area that we're having the bug in also, I might say that now would be a good time to switch so that we don't have to hop out there. Since we're not getting that bug in other locations, we might as well just start on the stairs. So we can just hop right up. It seems to mostly be about going down the stairs. And you can see there's just a little glitchiness. It's like things move, it moves to the right a little bit, which doesn't make a lot of sense. Because that wouldn't even, like, I don't even know how we would get that happening exactly. Like that's a saucy one. That's a weird one. Because if we're blending from, from this P to this P, I'm not sure how the T interpolation value could ever be something that would produce a rightward motion like that. Unless this... I don't really know. I don't have an idea about why that would be happening. But it does look like it has to do, right? With these two. It's not going to ever reset these. Oh. Right. That is what I had meant to type in. I meant if we move either of those two things, not if we move both of those two things. I don't necessarily know that that was the problem, but that was not what I meant to test for obvious reasons. So I'm getting even just there, when I cross the boundary, it's glitchy, right? I don't know. You may not be able to see that due to streaming effects, but when I cross the boundary, it glitches, right? So something's just busted. I'm doing something backwards or stupid that I'm not understanding there, right? And I'm not sure what it is. So again, in theory, if we map everything back into chunk space, we should not be having any problems with origin movement because everything gets encoded in the same place and then gets decoded in the same place later. So the sim region shouldn't be able to affect us here, if that makes sense. It seemed like in this case, we weren't really having much problems other than with this particular issue here. So in terms of resetting the interpolator, we didn't see this problem when we reset the interpolator only on room moves. I would like to do something here where I'm just curious, what happens if I... what happens, like, am I ever, like, not in a room? Because I don't know. Doesn't seem like it. So that's good. So we know we're always taking this code path for even when we're having the glitch. So we know we can basically read this out of it and just say this is happening. This whole thing, right? So we know we're looking at what the room looks like. We know we're setting up the new target P based on the center of the room, right? We're going to move the offset of that thing out from there somehow. We're going to reset the camera simulation center to be based on that simulation center. Yeah, all that seems pretty normal. And so then the only question here is like, yeah, I mean, one thing is if you're still in the middle of interpolation, I guess one thing maybe you have to say is if the interpolation if the target P changes discontinuously, then I suppose we kind of always have that problem. So I wonder if we, aren't just stuck back in the same position. Because now I think about it, this is going to have that problem, period. If we allow the target P to get updated, then it can always get updated out from under us. And if the target interpolation was 0.9, let's say, and the new target moved discontinuously, this wouldn't run because of this check. And so really, we're just going to have to deal with the fact that the new target moves. And yeah, and I don't really know what else we could really do about that. So in terms of this, what we would want to say is, look, if the interpolation is equals 1 and the distance we would want to move is greater than that, then we do, right? And I think we really don't need this extra check. I mean, that was probably a waste of time. I just wasn't thinking it through, right? But new target P really shouldn't be allowed to... it's got to vary more continuously, right? So when we set new target P, this thing here, we got to make that be something that's at least a linear interpolation or something, right? And so I think we do get back to what I was talking about here. Even though it seems like we could have handled it without that, I'm not sure we really can. I think we are going to have to do the sort of more fuller featured part where we deal with the continuously moving new target as something real, because we always could hop down like in some way that like we were doing there, where we kind of need it to smooth out those motions and think about them more critically, right? So let me just verify that that's the case. If I was to move new target P smoothly, would this work fine? Meaning if I was to say, take this delta, get the length of it, and then say if that length is less than some, epsilon value I don't care about, then just set it. But otherwise, linearly move it between the two, right? And so I guess what I would say here is maybe this is like the target speed. And whatever that's going to be, it's going to be like dt times something. So maybe the target speed actually is just dt. I don't know. So in the case where I would just move it however much I can move it or less, we just set it directly. Otherwise, I take the d target p times the max target speed, and I add that. Right? So I'm just moving the target like slowly, kind of. In that case. So this would only be relevant in the case where, in terms of moving the target slowly, if we've started a new interpolation, that's not necessary. So we really only need to do this in that case. So where we have done this, we can set them directly. So we can just do, that. But in the other case, we have to update the target continuously so that it doesn't cause a discontinuity, or something like this. So now you can see us having that target move around continuously, right? Which again is not, I think, what we actually want to do, but I just want to make sure that fixes the glitch bug, and it does. We do have a problem with, we want to, like I said, I think we want to make those alpha ranges be set more directly, because we really don't want them interpolating at a separate rate. So that was definitely the problem. And so now our question is just, well, okay, if we know we have to do something better here, what's the something better? Like, if we know we've got to have some way that we smooth this out and we have certain requirements for how we want our camera to behave and so on, what does that look like? So I guess my first inclination is to say, what if we made something where we look at the distance between where we would like the camera to be and where the camera is now, and we map what we would like the speed to be at that point. We map what we would like the speed to be at that point, and then we map that versus our current speed, and we basically make those two things match. I mean, one way to say that would be, right, so we've got 3 phases the camera could be in. We've got a min speed area, we got a like acceleration area, a deceleration area, and then a max speed area, right? And if we're far from the target and we've gotten into this region, we would just stay here. But then once we get closer to the target, we go into our deceleration region, and the speed should be proportional to this, right? I think we also want to try and get the velocity of the target. So we'd like to know how fast the target is moving as well, because we want to target where it's going to be, not where it is, because otherwise we're always a little bit behind, right? So let's see to what extent we can even get that information to start with. So in the entity, I don't actually know, we've got the DP value here, but I don't actually know if anyone is setting that value, like the P, DP, and DDP. I suspect they're probably not. So inside the entity, like, we never set that, right? So, we could approximate it by looking at the difference between last frame and this frame for an entity and say, well, we assume that the motion will be similar to what it was last frame. But that's still not quite right. What we'd rather have is some notion of the speed that's set by the actual controllers. So I guess I'll forego that part right now, and then we'll try to get that in later, because that'll be the harder part, since we don't really have a way of getting it directly. Okay, so, and we kind of do know that because, like, we have a permanent placement point for this entity, generally, right? There are world locations for each of these, I think, that we store at some point. Maybe not. I guess we only store those in actual stored entities, but so we'll assume we could do something about that later. But let's go ahead and look at this first. So if we want to do something more sensible here, then let's start storing some different parameters. The first thing I want to do is let this thing happen the way that it was happening currently. So meaning maybe let's switch back to inside a generic room. And so if inside this room, right, we can hop from here to here, and we get our ease curve the way we wanted. So let's recreate that ease curve behavior. Let's see if we can recreate that without using the from concept, and instead working mostly with accelerations. You know what I mean? So inside the world mode, if I was to store instead of a from P and a target P, if I was to, for example, not store the target P at all, perhaps, and I'm going to get rid of the from P and the T interpolation, but the target P, I'm going to say I'm going to keep for now because I don't know if we're going to need to track whether we're doing big movements or small movements at any given time. So I'm going to say we keep that. But from P is going to go away. So let's suppose we got rid of from P so we don't know anymore where we're coming from. And let's suppose we got rid of this so we don't know this stuff for the T interpolation, right? We don't know any of that. And we have to still do something relating to an update of this form. Okay? How would we do it? Right, so this is what we've got to work with. We're just getting a target P in here. And the only thing that we know that we can remember is basically like our speed, right? So we're not going to store our speed as a vector. We're just going to store it as like a single value that we say like how fast, like what's the throttle, right? And it'll start at 0 and go up to some max value. So then I'll say like max camera speed, something here, right? Or maybe I'll just say dp max. And the dp max is whatever it is, and that's the maximum dp we could get up to, and we'll set this value to something else later. Or maybe you want to, now that I think about it, let's not do that. Let's say the dp, let's say this is between 0 and 1 always. And then we'll just multiply it out, right? So we'll say 1 is maximum speed, and we multiply that by a speed coefficient later, but we always just consider it going between 0 and 1. Okay, so now let's look and get some information about our behavior here. So we know that we're going to target P, and we know we're coming from P. So this is the delta P, meaning it's not the derivative of P, but it's the total delta, right? It's how far we would need to go. You might even call it the desired delta P, or total delta P, right? So that's the amount that we would need to move to get the full, to just go directly where the camera system wants to view the world from at this particular time. So we know the length of that vector. And we can now consider mapping that into a space that looks like this potentially, right? Meaning we know how fast we could go. And so we could say, well, if we were at this location, where would we be ideally on this curve? Meaning, what do we want our deceleration region to look like in terms of something spatial? What's the distance out at which we would start slowing down? And what's the distance here where we would start accelerating, right, in this curve? You know what I mean? It's basically like, oh, maybe we do this over the course of like 1 meter or something. You know what I mean? So what we could say here is like, let's map into that space where we expect that fall off curve to actually be in terms of taking delta steps along it. And then we could, make that total work out. Seems plausible anyway. Seems plausible. So if we wanted to do that, then what we could say is we could almost make like a fictional construction of where we are on this curve and solve for that in a sense. I know that sounds kind of weird, but we could still update as if we were going to always lerp from location to another location along that curve, and we would just reconstruct what the location should actually be. You know what I mean? Yeah. That all seems pretty plausible to me. So let's sketch out what that would look like. If the total length here is greater than the cooldown distance, right? So whatever we want that, like, I guess whatever we call that, acceleration, deceleration. So we'd call this the decel range, right? So this is the range over which we decelerate. And who knows what that is, right? So maybe we say we've got an accel range of 1 meter, a deceleration range of 1 meter, right? And then we've got a total delta p length that tells us how far we are from the target. So if we're in deceleration range, we do one thing, you know what I mean? Otherwise, we do something else. So if we're in the deceleration range, then what we need to do is figure out where in the deceleration range we are, and that would set our deceleration. And in theory, we could just do that directly. So I think, and maybe this is just stupid, but I think what we could do there is say, whatever our deceleration range is, let's just always, less than. Whatever our deceleration range is, let's just pretend that we map the curve into that space and finish that way. There's a couple different ways we could do this. My thinking is that you solve the curve for where you are in the deceleration and put the p back that far. Does that make sense? Because we have one more piece of information, which is what the speed was that we were traveling at that time, right? And we know what that is if you look at, in terms of the speed of the t parameter, right? The delta that's being passed in there. I mean, we could even do it with finite differencing by looking at the two values. But in terms of getting the derivative of this t value, you can compute it directly by just saying, well, it's a times t times t. This was t to the third, so it'd be 3 times a times t times t, right? Plus 2 times b times t plus, c. So we can compute the derivative of the input value trivially. And since we know that these were constant values there, we know what the derivative is. It's just d blend times those values. Like we can do that derivative directly as well. So we'd be able to compute what we were actually using as a speed wherever we are on these curves pretty trivially by just setting d blend however we want. Just computing d blend whenever we want. So that should be possible as well, but I'm just trying to figure out how we would want to set this up. And it's kind of a little bit of a mind bender. So if you imagine us going from one location to another, then if you were to set up what the curve should look like there, you would want to set the maximum speed you were going to hit based on that distance and then do a little ease in, ease out of just that much. Probably, right? I would think. Meaning, like, based on where you are and whatever your speed was, you can then say, well, if I was going to assume that my speed was based on some other position, what would that position be? Right? So, meaning in this construction, if I take a look and my speed is whatever it is, x or something, right? Or s, then I know there are two places on the curve I could be, right? I could be here or I could be here. You know what I mean? And so if I look and I say I'm this distance away from the thing, I know that this stuff always looks a particular way. Then there are some ambiguities, I guess, which is like if you don't know whether or not you ever hit your max speed. So I don't know, it might behoove us to try and remember whether we're in the acceleration or the deceleration region. Meaning, if you stored your dp and your ddp, so you had both the acceleration and velocity, then you could differentiate between the acceleration region and the deceleration region by looking at what your GDP was. Yeah, and again, if we looked at the if we looked at the equations, you can figure out pretty easily what that's going to be, because if this was your equation, then again, I can just do the same thing. It's going to be 6, right, times AT, 2 times B, and this is just going to be 0. Sorry, 1, right? Is that right? Because, yeah, c to the first is 1 times c to the 0th, which is 1, which is just 1, I believe. That's my story, and I'm sticking to it. Oh, wait, no, that's a constant. That's not a variable. So it's just that. Right, it's c times t, so this is t to the 0th. So t to the 0th does not appear anymore, so it doesn't get a derivative. So I think we would know all these values and could store them. And so then we would kind of know where on that curve we were, I guess. I mean, the other question, though, is why wouldn't you just store t? Why wouldn't you just store what your t value actually was? And maybe that's a better idea. So it's like this is where we were on the curve. And I guess the reason not to do that is because as it moves around, you want to preserve, these are the values you wanted to preserve, meaning you wanted your velocity and acceleration to stay the same. You wanted them to match, you know what I mean? But you're creating a new curve, so you might be at a different place on a new curve, and the delta that you'll apply will be different. So you really want to match the actual physical values that the player can perceive, not the internal t value, which doesn't mean anything to them, So like I said, this stuff is very much more of a black art once you get outside of just doing froms and twos. Because you can see why there's a lot more complication here, and you have to kind of define something very nebulous as to what's supposed to be going on, and it makes it pretty hard. But if I want to push forward on that, right? So let's see what we get here. So what I'm going to do here is I'm going to look at the DDP and the DP values and stuff like that. I'm going to try and figure out what's going on in terms of how to apply those and go from there. Okay, so let's suppose that I am in the, I am looking at where I was. And I know I've got a DDP and a DP. Let's say I want to solve for the curve that would get me there and that has those two values, right? So I want to solve essentially for the, the V and U's that would produce those values. Now, I can look at this more as a 2D curve, but I don't think I want to. I think I just want to look at it as a 1D curve with a fixed shape, right? So I think what I want to do is try to solve, I want to try to solve this as a sort of puzzle of the form. Okay, I know that I have a curve. I know that the curve looks like something. And I don't know what this is. I'm going to call that D for now. So the length between here and here is D, right? And what I now have is I have a camera position somewhere along this, which we'll call P, right? Now, what I don't know is I don't know where I started from, and I don't know where I'm going on any previous frame. So at some point, the camera was like here and was asked to go to here, and it started moving, and it eventually got to like here at this speed, right? This is the speed. It eventually got up to this speed, and what I know is that it will continue to travel at that maximum speed until it gets close enough to the point to decelerate, right? This is sort of what I'm talking about here. And then when it gets to that point, it will decelerate down, and then we'll be done. Does that make sense? So I want to kind of solve for that behavior. And there's really one other annoying point about that. And that is if the curve was too collapsed. So let's suppose that actually, if this is those two regions, if they were to overlap like this, so you had, this and, oops, should draw that differently. So in this case, right, if I've got a thing that's like kind of going up like that, and then I got another curve that's kind of going like that, then there's actually a point here where we have a different max speed now because we can never get up to the other max speed. And I don't know what we want to do there. It makes a difference because if this is a constant versus a variable, it makes a difference. So if our max speed is something we always know exactly what it is, and when these two things overlap, then there's a discontinuous acceleration at that point. I don't know how bad that is, like one way or the other. I don't know whether we need to treat this as something that kind of goes more like that. You know what I mean? So I guess we'll cross that bridge, when we come to it. All right. So let's assume for something to start off with a little bit easier, Let's assume that we were always going to solve for like a single one of these, maybe, I guess, rather than the split in half one. So let's suppose we were always solving for a parabola curve. So we know that we're just going to do that. And so we have a particular location along the curve that we are, and we have a particular destination that we know we want to get to. And so the question is just where on the curve are we? So we want to solve for t in an equation that looks like this, right? And that's because we actually had an integral f here that was our original. Right? And so we knew that we took the derivative of that and we got this. So it's actually like that. You know what I mean? But it's of that form. It's a quadratic of that form. So if we know this value, if we know f prime of t, right, which we would know because we're storing it, it's the speed. If we know f prime of t, then we would know what t was because we can solve for t, right? It's a quadratic equation with a solution. And so we can do the, what is it? I don't even remember the quadratic equation at this point. It's like, you know, minus b plus or minus square root of 5 over 4ac, you know, some nonsense like this. What is it? No. It's something more like this. You know what I'm saying? What is it? Show me the equation, please. I was close. It's not c squared, it's b squared. So it's negative b plus or minus b squared minus 4ac all over 2a. It's weird how you like sort of vaguely remember these things when you haven't done math in a while. So I can solve for this, and I'm going to get two answers to where that derivative was equal to that value, right? So I'm going to get two answers to like where the motion, where the speed was equal to that. The reason for that is because, well, and I guess now I think about it, that's the solution if we are actually solving the cubic itself. But if you think about it, if we just want to know on here on the speed curve where we were, that's easier because the speed curve is actually going to be broken into two parts there, and we know the other derivative, right? We know we could store that as well, right? So the 6at plus 2b, we know that too. And so in a sense, we can just solve for that one probably, right? Couldn't we? If we just stored our acceleration, whatever our acceleration was. I mean, correct me if I'm wrong, but why couldn't we just say, here's what our acceleration was, and then get back the value? And that's simplest because that doesn't involve a quadratic equation. So I'm not sure why we wouldn't do that. That seems better. So let's say we just did that, because then we could solve that directly, meaning if we store this value and we want to know where in the curve we were on the new curve, so we're mapping from the old curve to the new curve, because it might be the same, but it might be different, right? Then to determine where we were on the curve, we could just map it backwards and say, well, we know A, we know B in this case, and so to map it backwards onto this curve, we would solve the equation for t minus 2b, you divide by 6a, so, you know, it'd be that. But the problem is that's not in world space, right? So that assumes that we were interpolating these two this way, and we need to actually look at what that speed would be. So there's actually a multiplier here of another value, right? And that value is this, is that whatever that stretch is. Does that make sense? So really the speed is this multiplied by the distance, right? So whatever that distance is has to get multiplied in here. So you might say the speed is 6at plus 2b times whatever this length is. So the length of like p target minus p current, or yeah, you know, whatever that is. You know what I mean? So if we think about it more from that perspective, so what we actually stored was this value and we need to get this back, then that's when this becomes a harder problem because we don't actually know what this value is either. So we really have two unknowns. We don't know what t is, and we also don't know what the distance is, right? Now, the reason we don't know what the distance is because the whole thing we're talking about here is to solve for what the curve would have been. So if we were to parameterize this on two things, the total length of the curve right? And then the t along curve. Then we know we can always perform our update as we wish, and we can store the information that we wanted to store, right? But what we have to do is we have to solve properly for these things. So if we have a total curve length, then what we would be saying is the difference, you know, the way that we're updating it is we have a t plus delta t, right? And so our f is this, meaning the amount of change is going to be t, whatever the time is plus whatever the delta time is, right? So if we want to know how far along the curve we're going to go, you know, and we've got, so in here, right, we want to figure out what's going on here, then, you know, in theory, this works. Meaning we just need to know whatever the function of t was at the time, plus whatever the function of the delta t was. You know what I mean? Now this we don't care about because this is where we are, right? This is just p. We don't need to compute that. So all we need to do is compute the derivative to move us along the trajectory we're trying to go. We know the delta t, right? Because the delta t is what's passed in. It's this value, right here. So that's a trivial thing to get as well. So really what we're talking about is what's the f prime? Well, we already said that the f prime, when you pass this thing in, right, is and you know what? I may have jumped the gun there a little bit. It's not that. It's delta t times f prime of t. My bad. Right? That would be the update if you're moving along it. And really, I guess I don't need to go that route because, again, if I know f prime of t, I can just set my location there, and then I just remember the derivative. So really what we're doing here is just using the derivative as a map. So all this is, we don't even need this for an update, and don't think of it that way, right? All we're doing is saving what this was so that when we do our next time, we will keep the same apparent change in velocity, so it's smooth. Does that make sense? So I need to know my f prime of t. So if I, and obviously my f of t as well. So if I'm going to update with an f of t, and I know that my f of t looks like this, right? I know that's what that looks like. But the way that's actually going to be interpreted is this way. How do I turn that around? So if I was doing this, and let's assign this to some value u for convenience. If I know that I have a p, from, and I was going to do 1 minus u times that, and then I was, because we're doing a lerp here, and then over here I was going to do u times whatever the target is. How do I rearrange that to only really talk about the change in those two, right? Well, if I multiply that out, I would get p of f minus u p of f plus u p of t, right? Which is another way of just saying p of f, I don't know if you can see this, I'm going to swap these around, plus u pt minus u pf, right? So it's really just p of f plus u times pt minus pf. So my update function, because this is where I'm coming from, right? Wherever it was. Excuse me. And this is where I'm going to. So my delta update here in this case can be phrased in terms of the difference between these two values, which I could just consider a single value for all intents and purposes, right? Meaning, trying to think of how to put this into a phrase that makes sense. This value is the entirety of what determines my velocity, I guess is how I'm trying to say it. The derivative of this is nothing. It doesn't have t in it, because u is the only thing that contains any t's here. Probably shouldn't use t for that. So if I consider this to be some p from value plus a u times some delta value, right? This is some delta p value, okay? Then I know that this is the entirety of my derivative function, right? So my f prime of my t here, or, and I can start from here. My f of t, if that is pf plus, and remember u is this nonsense up here. So it's at cubed plus bt squared plus c, right? So if this is the way I phrase my function, start at the starting location, which we don't know what it is, right? It's just somewhere that you started from, we don't know. Then we're going to do the update here. The nice part is, once I take the derivative, if that's what I'm mapping from, this goes away. And that was what I was trying to get at. So we're left with effectively two unknowns here for our purposes, because delta p's direction is known. It's always in the direction of the target from where we are. So the only thing we didn't know is how long is it, right? And you might say, well, you know how long it is. It's just how long from our current location to where it is that's the length. No, because we're talking about a curve that may have been executing for some time and we're in the middle of it. So actually this extends behind us, and that's the whole thing that we're trying to get to, right? So once we take the f prime of t, then what we're going to get here is this is effectively a scalar value. So we have delta p, let's pretend it's in the front, times all of our junk. And, excuse me, in order to do that derivative, it's pretty simple. We can still do exactly the way we did it before, because this delta p can just multiply into everything, right? So we would just have delta p at cubed plus delta p bt squared plus delta pc. And let me just get rid of that for a second. Right? This is not varying, but it is a variable. And so when we take the derivative, we're still left with the exact same answer. It's 3 delta p at squared plus 2 delta p bt plus delta p. Okay. So if we store both of these things, which again we can take it again, so if we store both of these values, we would have two equations in two unknowns, and we could get back our t value, right? We could get back whatever the t value was supposed to be, and whatever our delta p value was. So if we want to match the velocity and the acceleration, what would our delta p have to be now? And what would our t have to be now to produce that answer? Right? So it's somewhat nasty. Like, I'm not sure we really want to do this because it seems kind of crazy, but not sure what else you would do. It seems like you would have to solve a cubic here, which doesn't seem good. You know, maybe that's not true. So I'm not sure how you would go about actually solving this. You know, if you look at this equation, if you solve this in terms of the quadratic, you would get t equals, you know, negative b, which is this term. So negative 2 delta pb plus or minus square root of b squared. So it's that again. So you would end up with a delta. You would end up with a delta p b squared. Right? Minus 4ac, so you'd have delta p a, or a delta p, c is just delta p, so it'd be, again, a delta p squared in there, over 2a, so 2a delta p. So you'd end up with something like this for your solution for t in terms of delta p, which is not pretty, as you might expect. Now, there are some nice aspects of it. So since there's a delta p squared in here, that actually would pull out of the root term, I believe, because inside there, what you're actually left with is delta p squared times b squared minus 4a. And so the square root of that should distribute just fine, right? So you should be able to pull that out and effectively get rid of it. And you know what? That's actually obvious. So the reason that's obvious is because if you look at what happens here, there's a delta p in every term. So you could have just divided the entire thing by delta p, and you'd be done. So actually, it doesn't depend at all on that, I guess, unless I'm wrong, which means you actually can solve for the t without knowing what that delta was. Sort of. No. You know why? Because we're not solving for 0. That's why. What we're actually solving for here is a value that we had before. That's the problem. So, you know, in here we're going to have some value that actually we want to maintain. You know, whatever the previous value was. You know, call it whatever you want. Call it x or something, right? So since there's an x here, that x value, which is the value that we're solving for, comes to the other side. So you've really got an an additional term here, which is that this c is minus x, right? So in the 4ac, you'd actually have two terms there. Yeah. So again, it's just pretty nasty. I'm not sure. I mean, we can solve it, and we could use computer algebra system to solve it too, so we wouldn't necessarily make any mistakes. But it does seem a little overcomplicated for what I would like. You know what I mean? I would like to just be able to say, look, let's just map this to a curve that would make sense for where we are. I don't know if that makes sense. I can't think of any other way to do this. I don't think you could do this. Meaning, I don't think if you look and you actually stored this instead, which would get rid of the actual t values, so you'd end up just going, hey, whatever your triple derivative is takes t out, and so, you know, you've got, you've got a correspondence between your old 6PA and your new 6PA, and so you just solve for that first. I mean, I guess one thing is, could you just store what the length was last time? And then when you go to use the length this time, you just look at the difference between those two things to determine what you're going to do. Yeah, I really don't know. Hmm. So I guess what I'm leaning towards is suppose I were to store where I was on this and its derivatives. And I just said I want to, or maybe I just said I want to construct something such that the derivatives match, maybe. So, the idea here is I want to make sure that, f prime of t. And what if I were to say that t is actually going to be something that we know what it is? So we're always looking to take the same step. If I only wanted to do delta p, right, that would be easier. Basically, if I can specify one or the other, it makes it extremely easy. The problem is having both. Trying to figure out what would happen seems bad. I could try, if I formulate this, I could try just seeing what the solution ends up being if I just let it plug and chug. So I don't do it, because I would definitely make a mistake if I tried to go through that entire thing, especially on this kind of large blackboardy thing. It's bad enough on a piece of graph paper, it'd be awful on here. So if we were actually going to call this, the function this, what would happen there? So if we were trying to solve this to maintain our velocity and our acceleration, and so we actually had all names for each of these things. So let me try to make it a little bit more concrete. So if I say my f of t equals the initial position plus the delta p, right? I don't want to call it delta p because that's going to be hard to put into a computer algebra system. So I'm going to call that, I guess, d for delta, right? Times my t terms. So I would say at cubed plus bt squared plus ct. And in our case, we don't really have a ct per se, do we? I think we set that actually out to 0. So, oh no, it equals, no, it does, it's 0. So there actually is no c term, but we'll solve for it anyway in case we want to play with those, I guess, if we're going to be computer algebraing it. So our derivative here, as we know, is going to just be the derivative of this thing with d tacked onto it, right? Because d doesn't change. I mean, it's not a constant, but it's not a variable. I know that's a weird thing to say, but it's not, it's like a partial derivative in this case. It's not relevant to the thing we're actually solving. So, in this case, we would say, okay, it's 3 dat squared plus 2 dbt plus dc. And we know we want to solve that for some previous acceleration here. So I guess, I don't know what we'll call that, but I guess we'll call the derivative of t, we'll call that u. So since we want that to actually be u, in this case, we want to say it's 3 dat squared plus t dbt plus dc minus u. Then if we take the derivative one more time of that, right, then that is 6dA plus 2dB, and that all goes away. This here is 0 and 0. And so these are the equations we're trying to solve. This has a t in it, right? So looking at this, I guess, I don't know, maybe did I make a mistake here? But it looks like actually for the double derivative, this is going to be set to something too. So maybe we'll say that's v, right? So if we are recording u and v and we want to match them, we end up with this equation, which actually is quite easy to solve for t. Right? So, that part's not that hard. It's only really this one that becomes a bear. So let's double check our math there. Let's get a I guess does Wolfram Alpha the best place to do this? I'm not sure who's the best to solve here. I don't know how we tell it to solve multiple equations. Yeah, here it is. So I guess you do like commas here. And I'm not sure how you specify what you're trying to solve for. It looks like you say for after it. So I guess you would say for x, y. That seems right. So we have two equations. Here they are. We have, and I guess we can just write it directly, which is u equals 3dat squared plus 2bt, dbt squared, not squared, plus dc, right? And then our other equation is v equals 6dat plus 2db. Oh, those don't appear. It's not what I wanted. So we want it to solve for d and t. Okay. Did I do something wrong there? Do I need to do this? Any better? This always happens when I try to use computer algebra systems. I never know how to get them to do what I want. So you can see how ridiculously ugly that is, right? It don't look good. I mean, there's the solution. And maybe we should just try it, but it doesn't seem like a good idea. And debugging it would be a nightmare, right? Because it's not an intuitive, like there's nothing you can really pick out about this. When you look at what it might mean, you've got like sort of maybe a little bit like the combined length of the AB vectors here, and then some, I mean, yeah, it's not really, I don't see a lot of way we would build a physical intuition out of that. And Mathematica is horrible for that. Like, it's really hard to get it to give you something that you can then reason about. It just kind of dumps out a giant scalar nonsense about you, and off you go. So I don't know. I don't have really any good ideas right now. I feel like I want to percolate this on this a bit. I guess one other thing we could look at is maybe what if we looked at it more like we just want to have a consistent way of accelerating and decelerating that follows our curve, but we just always map it into the same size curve, and we just say, well, wherever we would want to be on the curve, we figure out that location based on where we are now, and we step based on that curve. So we just look at our current velocity, and we just solve based on that. Because again, solving this just for one of these variables is actually much easier, right? If we just wanted to get rid of the d, you know what I mean? If all we were doing was solving for t, then it's really straightforward. It's just a basic quadratic, and you could even solve the acceleration instead, and then it's not even that. So 60 at plus 2 dB, right? If we just said, well, yeah, okay, so it's v equals 6 at plus 2, like that, that's even easier, right? So if we wanted to just say, look, we're not going to try to be that fancy about it, so we're going to just store our ddt, and we're going to map that back into wherever we would be at the current time on the curve that is where we are, I don't know. But, we want to be able to step towards the position as if we knew where we were, on the curve, as if we could. Yeah, as if we could just take that step. Let me just try that a little bit and see. So let's suppose that we stored the dte and the ddt. So what we're storing there is basically saying, look, we're just storing on the curve where we were. I mean, I guess what you could do instead is just say, look, we just store what the t value was that we were trying to be at. Maybe. So we do keep that t interpolation around. Like maybe we look at that. And then we say, all right, when we're going to interpolate here, we say, how far away are we? We know what our parameters would have been last time. How far away from this are we? Do we need to switch to another part of the curve? Or can we keep going with this part of the curve, right? And once we get up to a certain speed, then we know we can just keep going at that speed. I mean, that's really the only idea I've got. And then when we get close to the end, as we're looking at those t updates, right, we're just looking and saying, well, we know we're on the downward slope, so we look to see, how far away is the thing that we're stepping to, and we just fit the curve to that. And as it moves, we just move it as well. I don't know. It seems underdefined still. I'm really having trouble coming up with a good. I know that I have literally never seen a good solution to this problem. So I'm not surprised it's tricky. Like, I've never seen a good universal interpolator. They're all pretty bad. And there's a lot of kind of crazy stuff you can do with them, which is like there's actual like more statistical fitting model kinds of stuff. You can also, like, we've done proportional derivative controllers before, and then there's also things that use sort of like noisy things that try to predict under noise, like where things are going, and then it tries to fit that. We could go that route too. But I was hoping to try and see if we could maybe push through to something usable on stream, because like I normally do on Handmade Hero, I try to work through stuff myself so you can see the process of it. But we don't always get to something good. And in this case, I'm really not seeing the something good from first principles on this one. So I guess one thing I could do is say, I know the length. I could always store what I thought my interpolation was from last time. And I could always store my t value, right? And I could just say, well, I'm going to adjust those two things heuristically so that as best as I can, I produce as best as I can, I produce a smooth value. So you've effectively got, two values that you store. You've got what you thought your length was last time, and you've got what you thought your t was last time. And you're just going to update those two values heuristically to try and, make it so that you're always stepping along a reasonable curve. It's not good, but if you imagine something where instead of this construction, like I was saying before, if what you did instead was you said, well, we're going to take a step, right? And the way that we're going to take that step is we're going to say, look, I want to go whatever the blend value is here. I want to do the step that is along that I want to step that far along the line, however much my blend value tells me to step, right? That's restructuring the thing in the old way where it's, if I have 1 minus u times target p plus u times from p, which, oops, it's backwards, which was the lerp we were doing. That's just the part I was saying before about how that's from p minus u times from p plus u times target p, which if you then pull out the u, it's just from p plus, you can see in here you've got here we go. If I rearrange these two terms here, if I just pull out the u, I get a u times target p minus from p. So if I said that I was going to parameterize it along those lines, then what I can do here is say, well, let's imagine that I had the sort of normalized direction vector. So, I've got some dir, and that's always correct. It's whatever the total delta p is, it's always that direction. And if I don't have one, then it's just 0, right? So I know what that is, and I know that my update is always going to be along that line, assuming that I have to update it all. And so in this case, I know that this would always be some blend value times whatever that length value is. So for example, total delta p length, right, in this case, times the direction. That's the actual update step based on the blend. And so then what I could say is, well, this can be a parameter that I'm playing with, and that I can store from frame to frame. And my t value can also be something that I store from frame to frame. And then it becomes a bit of finesse about which one, about how I update them, right? So in this case, it would be something like this. So, if I was to store these two things, and then adjust them, so, maybe we get a delta p in here like that, and then I'm actually storing it out this way. And then the question is, like, how am I actually going to produce those things? So, you know, then there's some update that happens with these things, but then I still always take the same step this way. And the dblend and the dd blend maybe, you know, don't need to be there. I mean, I can leave them in because they're valid if we ever want to use them for some other reason, but then we save them, you know, and off we go, right? So if I want to update that based, you know, in some kind of sane way here, where I know that I'm getting these two things and then I want to do something with them, right? Then the first thing I could do is I could say, well, look, if I was going to use this, would it be a sensible thing for me to do to just use whatever it was last time, right? So meaning when I go to take this t value and I want to move by whatever the delta step is that I'm asked to move by, whatever that is, you know, if I do that to update this value, and then I'm going to look at what the actual change would have been, and I probably want to do this, right? Another way to do that, I guess, would be this. So, you know, if I get the t value and I update it this way, and then I say, well, you know, what if I actually just plugged in that t value here? So I said, you know, I'm going to get this out of it. What would that, you know, what would that give me? You know what I mean? So this is not entirely correct though here. So yeah, like one of the problems that we would have here is this construction isn't quite right because we don't know exactly where the you know, where that delta p would have actually placed us. So, you know, really we need to say something more like this. Yeah, so the target P minus the direction, like, yeah, I mean, even if we did that, I'm just trying to talk this through. Sorry, I'm thinking inside my head here. We can't actually do it that way because we don't have the from P anymore. So we would have to turn this into something that was a step that was based on back projecting where we were and then taking a step forward towards the goal from there. We don't have from P here, and it's not actually this, because, right, if it was that, then this delta P value would have had to have changed, I guess is the way to look at it. Yeah, I don't know. Not feeling it here, folks. Not feeling it. So, trying to think through some other options. I mean, one of the things we could say, I suppose, is if we start our target in velocity and we always assume that we arrive at the target in 1 second, right? Or some time, right? No matter what it is. then given our current velocity, what is the curve with this particular velocity that would give us that? And because we don't have t, the t is not really I think that still gets us back to having to solve the quadratic. Because I don't really see any way of making that simpler. Because you're always going to need to know those two things. I mean, I guess. So here's a super crappy way to do it. If we actually just assumed, generally speaking, that we were going to set the t value, and the t value, or rather, we were going to. Yeah, no, I don't know. I have no good solution to this problem other than the nasty solve. The nasty solve is the only thing I could think of that would let us actually produce the thing that we want, which is to figure out which other curve we could be following that would place us there, pleasantly, right? I'm just trying to think of any other things that we could really do there, and I can't really think of what they are. Another way to, I guess, parameterize this would be to say, like, what if we just had a velocity here, and we were going to say that the velocity is updated based on a curve rule, so that we have to solve for something that will produce that, but that's the only thing that we solve for. So, like, if we know that we have some kind of an update rule that just does whatever it does. So, we've got something here that produces our dp, and so it's something along the lines of what this would be doing here, right? So it's something along these lines. Where we produce the D blend, and then we've got to figure out what the we're always going to actually still be applying this thing as one of these. So we're going to actually take derivative-based steps. So we're never going to try and look at the first order curve, or the zeroth order curve. We're only ever going to actually use an actual dp. And then we're going to store the dp back, right? So we're doing a more traditional update step. We don't know what t was, right? But we're basically we're just trying to compute a dt dp pair always. So the dt we know, and the dp is just something that we're going to try and compute to give us an update step. And we're going to do it in the standard way where we would say, in the case where we would arrive at the target exactly, we're just going to get there directly. But in the case where we wouldn't, then we won't, right? So, if we say, well, the total delta p length, if that's less than the step we would have taken, so like if that's less or greater than dp, I should say, then we actually do our update, but otherwise we don't. And again, this always happens in the direction. So, we're gonna step in derivative space. We're gonna have the target p here, and blah blah blah, and we're gonna back assign these, right? And so in this case, we would assign whatever we did use as the dp is what we'll use again this time. And in here, what we'll say is, well, whatever we used as the dp is now 0 because we have reached our target. So we're killing our velocity entirely, right? Make sense? And so when we come down through here, we kind of don't really know what we're doing. And we don't really know how we're going to produce this stuff, right? But if we look at how this would get produced, then really what we need to figure out is, so that is not used. Yeah. So really what we need to figure out is how we would be producing this dp, right? And so if we set the dp to like the total delta p length or something like this, right? And if the dp was greater than our maximum speed or something like that, and this is actually times dt, right? So this is, I guess you could call that delta, that's the delta p. So it's the actual time step that you're taking, the actual amount. So in that case where we're actually going to take the step, we take the step, otherwise we set it to 0, right? And so here what we would say is, well, the dp is going to be equal to, whatever the maximum speed is. In this case, I don't know, if it's over 1.0, then it just equals 1.0 or something like that, right? And that would give us a linear blend, right? Like we had before without the curve. In theory, anyway. Well, if I haven't typed in something wrong. It gives us a very slow. Okay, that might be excessive. So let's say it was 10. Let's make it faster than that, right? So there's a speed 10 version. And actually, I guess what I really want to do is that. And so there's a non-good version, right? But we can see that the update is at least happening properly. So now the question is just, all right. We know we had a lot of trouble figuring out how we might compute this value. But what should dp be in this case, right? Like, what do we actually want our derivative to be? Can we compute that from some curve that we compute more heuristically if solving it is going to be pretty nasty, right? And unclear if we really want something of that complexity operating in here where we can't really form a geometric understanding of it, right? So if we want to update that a little bit more directly there, and just play with it more directly, then what I'd want to do here is say, well, I have the dp from last time, right? So what I'd like to do is I'd like to make something where we're going to be stepping along a curve here. So I'd like to make some way of figuring out where on the dp curve we were, based on what I'm going to construct to create it, right? So maybe I just do a series of constructions on curves to try and solve it and see what would happen in that case, And so, if I was going to construct a curve onto the target P, maybe I can try constructing a curve that's a deceleration region. So, maybe I look at it like this. So if the total delta P that I have to go is greater than some maximum, then I want to accelerate up to my maximum speed, right? So I'm trying to increase my speed. So, you know, I've got my accel range here, right? So if I know that I'm greater than my acceleration range, so maybe I'm over, 1 or 2 away, then what I'm trying to do is I'm trying to fit myself to where I am on an acceleration curve, right? So maybe I say this sort of thing. If I'm greater than the combined of these, then I'm just trying to fit myself to a curve to figure out where am I in an acceleration curve. And the acceleration curve is of length this. Okay? So what I would do is I would solve with a known length this equation for t, right? Which I already know is easy. It's just that. You know what I mean? So actually, I guess I'm solving for t here. So my previous dp, which I guess I can pull out here. My previous velocity that I was, if I solved it this way, I would get what the t value is by saying v minus 2bd, right, over 6a. And so if we look at what that gives us, we know what a is, we know what b is, and so d in this case is the only thing we don't know, but we do actually know what it is. It's the acceleration range, because that's the curve that we're mapping it into, right? So we're going to say, let's map ourselves into, and this, by the way, is the dp we're solving for, right? So let's solve for the t that we should get there. And then what we want to know is, let's get what our velocity should be now at that point. So what should dp be if we were going to map it up, right? Like, what would it be? And so in order to get what that dp should be, now what we want to do is feed it back into this equation and get what the actual derivative was at that point, right? So we want, whatever our accelerange value is here times whatever the derivative of this curve is, which is this, right, for that given t value. That's what I would argue, right? Again, we know a, we know b, blah, blah, blah. So the only thing that we didn't know here in this case was t, and now we've done that and updated our dp. So then we're saying, look, that's what the derivative should be. It should be this, because that's the derivative of what the actual function was in that case. Right? I mean, I think that's roughly correct. And then we would say, well, okay, well, in the case where the total dp length is actually less than the deceleration range, so, I mean, I guess we could even say, look, if it's less than the deceleration range, here we're going to do this sort of thing, and then we're going to say, look, as we accelerate this t forward, we know we never want the t to go past 0.5. So we would essentially say, like, if t is greater than 0.5, t equals 0.5, right? Another way to say that would be t equals clamp between 0 and 0.5. Meaning, look, we're going to accelerate to max speed if we can, and only if we're inside the deceleration range would we back down, right? Seems what we would want to do. So everywhere outside of there, the acceleration range, we're going to map into where we were, and then we're going to move forwards by some amount you know, to move our t forward there. So this goes away, and this is like that. Right? I think. You know, don't quote me on that. So in this case, we're just going to say, look, let's recompute this thing with a known range. And this is kind of just maybe saying, look, we're just going to use the t acceleration value in this case. And if we see that we're less than it, then we're going to solve that. We're going to use the same dp to solve back into a deceleration curve, which might not be what we had been doing, but now we've fallen into the deceleration range, right? And so now what we need to do is when we're in the deceleration range, we need to say, what was the t that we were at for that level of deceleration, given what our distance is now, I guess. I'm not sure what we would do. I guess if we're inside the deceleration range, we just do the step without doing the dp consideration, maybe? Meaning if this is actually true, maybe we map the t and we take the t step based on distance instead. You know what I mean? Instead of by t. So in other words, here, instead of solving for t, if we solve for d, meaning we solve for distance now, and I guess that's not even really a solve. That's just saying, look, let's map how far we are. So our t, you know, I guess we're really just saying, look, take whatever the t value is, which is going to be our total p length in this case, right? And then we would take, so that's how far we are, and we want to map that into our deceleration range. That's our t value, right? And we're just going to step it forward. Now, we want it to actually be a strictly decelerating curve in that range. So what we would want to do there, I think, is say, well, we're actually going to step down from, you know, we're actually shifting this so that we start at 0.5 and go, so we really want that, if that makes sense. Oops. And once we've mapped that, then we're just going to take the actual t-step directly. And we don't really need to do this. We could just take the t-step directly, but I guess I'm not going to do that right now. That's absurd, probably stupid, and it probably won't work. Just for the record. This stuff will want to work in a slightly different way. So for right now, what I'll do is I'm not going to blend those. Because we will want those. I also think we probably, like as we were seeing, we really don't want those blending separately. We want those to blend, oh well, you know what, I could actually just do this. We actually want those to probably be set directly off the camera because it looked like they really shouldn't interpolate on their own because there was like some bad effects that looked like they were happening there. All right, so let's try and get this working now. I'd like to have it sort of at least working crappily, and then we'll pick it up again on next stream. So this actually takes the dt into account here. So I guess really... No, I think that's all correct. But the decel there needs to update t. Right? So yeah, looking at these as we kind of move along the curve there and get whatever that derivative should have been. Um, I don't know if this should really just be computing the t equation directly, because now that we're moving along the curve, the dp is really just a residual value we store for solving. So it seems like a waste to do it this way, but I'll keep doing it this way for now. But that looks fine. Yeah. So I feel like that should be okay. So I'm not really sure why we're not able to get any motion there. I guess with a max speed of 1, that's not great. So, I mean, you could also say, well, this is probably not great. I am interested to know if we're just getting a slowness factor there. But we'd want to push that back into the thing. So it sort of works. It's not good, but it sort of works. So okay. So looking at the accel and decel range there, and just thinking it through a little bit better, I'll probably leave thinking about this because I want to percolate on it and think about what we might be able to do here that's a little bit better. But yeah, in terms of acceleration, we should have seen that kind of come up to speed, like... I'm not sure why we were seeing what we were seeing there exactly. Like, we should have seen that come up to speed a little more gradually because the dt here is in real time, right? So this is going to go over the course of a second, right? And this should solve back into the same thing. Oh, although, are we solving the... Did I solve the wrong thing there? That's the derivative. That's not the velocity. That's the acceleration. So I did actually do that slightly wrong there. It's really that we had done the equation for. Which, yeah, I guess I don't know any particular reason we can't do it that way, but that is different. We could do this a lot cleaner. In fact, we can pull these two out. You can see they're computing the same thing. So all you really need is the t. You know what I mean? And the range. But I'm not gonna do that quite yet because we don't really know what we're doing here. So if I do that and then store the ddp instead, and the dp is only used for the computation, You know, maybe that's a little better because we were using the wrong thing there. But I don't know, like I hacked that in pretty quickly, so there's probably other problems. It seems like we're not really getting what I expect though. And like, I don't know what's going on with that. I think that's just these. So what I could do is change those, you know, while we're playing with this, I could go ahead and change the fog and alpha spans to just be like out in the middle of nowhere. You know what I mean? Yeah. It doesn't help that we get jerky frame rates that I'm not really sure exactly where they come from at the moment. Possibly the fact that we're a little too stressy on the graphics card, but I'm not sure. But you can kind of see it has a hitch in there too. So yeah, so just thinking through what we would want to do here. You know, during the acceleration phase, right, we're basically saying, look, we want to try and get up to the speed here. So we see like where we were at, and then we would figure out what we would want to compute based on, oops, don't ask me why that's that way. And then in the deceleration range, we would just say, all right, map us into however far away we are from the target we're going to, and we'll just slowly, you know, kind of decelerate there. And if we wanted to, again, like I was saying, we could sort of make this thing just actually take the step by reverse computing what the t actually is doing and doing the lerp, right? So, you know, in here, we could just say, well, that's what the DDP is for placement, but, you know, we want to actually do the lerp here. And we do know where we're going, right? We're going to the target P always, and we're going from the target P minus whatever whatever the size of this curve was along the direction, right? So we want to lerp from whatever the decel range. We want to lerp from here to here using our standard t value, right? And so in order to produce that smoothing, we need to do this. But it would just look like that. Then to produce the value that we retain for future solving, we would just say, well, the deceleration range is the multiplier, and then the 6 times a times t plus 2 times b. That's the sort of the version of this that gets us our derivative, right? So, you know, we could do that, and then you know, in here where we're actually doing where we're still doing sort of that update, I think that just works okay, probably. But the DDP part of it, again, is just going to be, you know, this here. So yeah, so looking at the acceleration range, if this is the acceleration range, this is how many units we want to accelerate over. You know what I mean? Then that's how that would work. And then down here, we would have 2 of these. In the acceleration case, like, you wouldn't have to do that. But in the deceleration case, you would, right? So you would essentially have this. So either we get there and this is 0, because it would just be t equals 1, which should in theory give us 0 for this, because that's what that's set to. So in theory, this should be actually the deceleration range version should just work. And the acceleration range is the only one that actually needed to destroy this value, right? But I'm just trying to look at this here. So yeah, so looking in here at the range we want to accelerate over, there's also, I suppose, in addition, it's really not clear to how fast you want to do those two things. So you have a speed as well of how you want those to go. So in the deceleration version now, where it's actually just stepping directly there, I'm not sure. So this is a little bit off. So if we take the total p length and we look at the deceleration range, and we're going to say we're going to map it into that space, right? So this is the part of the curve that would be decelerating. Then this part is actually needs to be to that range, because we're only taking the halfway. So we're actually lerping such that it starts twice as far back as that. I believe that's correct. So I'm not sure, again, though, why I'm getting that. I think I may have made a mistake in this one. So let's make these a little larger just temporarily. So if we're within the deceleration range, we map the t so that we're getting the deceleration range to basically be half of t. It goes from 0.5 to 1. Right. Then I want to blend there, and I want to say I want to lerp to the target p between these two things such that 0.5 is actually where we would start on this. So the deceleration range times the direction times 2 is actually back where we would have been. We use the blend this way to go into the target p like so. And then we have the ddp equals the deceleration range times this. But again, that actually is wrong too. So that actually needed to be 2 as well in there. So I guess that's about right, maybe. But it still is good. It doesn't seem like it's really working at all. So I think I've got something very buggy happening there, but I'm just not sure exactly what it is. Oh, weird. I'm not actually updating the camera's position here, though. That was weird. So what was it doing in that case? What is going on there? I'm going to nerf this case at the moment, by the way. So what am I doing weird there? So I'm lerping between this location on the target P, and I'm using the blend value for that. And I know that this has to be something between 0.5 and 1, so I know my T value is something reasonable, right? So that seems fine. And really, so I don't know. I don't see a lot of issues with that. When I do my lerp here, the GDP value isn't really used, right? So that's not getting used because I'm not hitting this case. So I don't really understand how I'm getting that behavior. What am I doing wrong there? I'm doing something really wrong. Because I should be able to map that in, right? I mean, there's nothing weird about what's happening here. I don't think. You know, that should be really straightforward. So I guess the mapping here is a little bit possibly wrong, but I don't think it actually is. I mean, I guess the way you could write this instead is to say that if it's less than that, then you're going to map it into the actual double deceleration range. Right? And so when you map it like that, but when you do this, you're gonna naturally have to, it's gonna work out to the same exact equation because you have to offset it because you want the back half of the curve, right? So I mean, it's gonna be that one way or the other. I mean, that is the t value that you are along the curve. And then the clamped t value is just saying, well, when I update that, I had better not go over 1. That all seems fine too. The blending value is literally just computing the straightforward blend. So it's just doing the exact blend we were doing before. And then the lerp is just using that value to get to the target. So as far as I know, like, this is the only thing that could be wrong. And I guess there's plenty of opportunities for that to be wrong. I mean, if I'm going from the target position minus whatever the direction is, times 2 times the range. Oh, I do still have to do the solve, right? Because that's not actually correct. That would only be correct if the speed was linear. Right? So that tells you your linear displacement along the curve. So you do still need to do the solve, right? You need to be able to solve for t along that position. So if you map where you are in the deceleration range, that only tells you what your output t, that's this equation, right? But it doesn't tell you what your input t would be. So you probably still do want to solve it this way, because if you don't solve it that way, you're in kind of a world of hurt, right? I'm trying to think if there's any other way to solve it. Because you'd have to solve a cubic, wouldn't you? I mean, you'd have to solve at cubed plus bt plus ct. So yeah, for that deceleration, I have no idea how you do that without doing a cubic solve. I tell you, man, this stuff is really nasty. This is why most people just strap proportional derivative controllers to everything and call it a day. Is because actually trying to get something that has a predictable curve behavior turns out to be really nasty. So I guess what I could do is I could solve for the curve that's at this, starting from this point with this velocity and hits the other point with the velocity of 0. What would the curve be? But I still don't really know how far along that curve to step. But what I mean to say there is I could say, well, during the deceleration phase, if I wanted to, I could do something like say, well, I know I've got, this construction that I did up here. So I know I've got this. And I guess what I would say is if I wanted to have the acceleration that I have currently, and I want to end at 0, and I know how far I have to go, what does that curve look like? And so that would be saying, like, okay, I guess that would be saying, okay, I know that I want to have an acceleration proportional to this t value anyway, because I know I can't really solve for the actual t value without a lot of stress. So I do still want to produce the value as a dp value, and the dp value is going to be whatever you would expect it to be along that target, but then you'll overshoot. I just do not see any good solution here to do it this way. Everything really wants you to solve a cubic or specify time. I see literally no good answers. I'm gonna have to perk on it. I'm gonna have to see if I can come up with something that I think would be reasonable here. We can always fall back to something that is basically just a proportional derivative controller. Which we can clamp out and probably be fine. It would have been really nice if we could have found something better than that, right? I would have preferred that, certainly. If we did want to do something like that, then it's easier, right? If we do want to sort of not try to have a resolved rate curve, proportional derivative controller update steps are very straightforward, which I guess is one nice thing. And I guess I'll put one of those in for now because I would like to end the stream with having something reasonable in place for that. And so if I get rid of all of that stuff that we were doing there, what I want to do here is look at the DP. And I want to match my target's DP ideally as well. And so we kind of need to get that value from the game at some point, and we're going to need that. But so we're going to need a DP of the target, and right now I'll set that to 0, but it's going to give us bad behavior, And so we're going to have to, get that out. But the proportional derivative controller construction you've seen me do many times before. It's not very complicated. All you're effectively doing is doing an update step that you would normally do in anything else. I'm not going to do it. I'm going to compute it in 2 steps. So I'm going to compute the DP first here. And this is going to be the speed. So I might say like it's just a velocity value. So I might call it that because it's not the actual vector, if that makes sense. But we're going to compute a DP vector here, and then we're going to update it based on the time step here, right? And so I'm going to use the same construction that I used before, which was this. And the reason that I'm going to do that is because I want to know, in this case, if the length of the thing, if the amount that I was going to step by is going to exceed the distance that I needed to go, then I'm going to actually do something more like this, right? So in order to produce the DP, the actual speed value, it's really just a measure of the distance. So it's the target. It's it's the delta that I need to go here, right? And I guess, now that I think about it, I could probably produce it this way. So maybe I take it back. I can just call it this. So the difference between where I'm going and where I'm trying to go to, right, whatever that value is, I apply some kind of coefficient to it. And that is my, sort of A coefficient, right? And then I've got another term, which is a term that specifies how I want to adjust the target velocity. So whatever my current speed is that I was using versus the speed that, that the target itself is moving. And this is going to be what my acceleration value is. So actually, I guess I should have written that as a dp there, right? And so I want to remember what my actual dp is, and I guess I want to be able to, feed that back in here so that I can can update it, right? Does that get written back? Yeah. There we go. All right. So using a simple update step like this allows me to set 2 tuning parameters, and those tuning parameters are how much I want the velocity difference to be accounted for, and how much I want the positional difference to be accounted for, right? And so each of those terms comes, as I get further away from the target, this term becomes more dominant. As I get closer to the target, this term becomes more dominant because, this one starts to fade away. And it's more about the difference in velocity between the 2 things, which this oftentimes will be 0, and this oftentimes will be larger because I'm trying to get those, to line up and to come to rest. So typically what I want to do here is I want to say, well, whatever the difference is in these 2 things, I want to match the speed of the target, which is going to be 0. So this value is actually going to penalize me for going too fast, right? And we're going to have to play with these 2 values and see what we want them to actually be, right? And we got to actually get this in there at some point. So now in order to produce this actual, make all this work, right, I've got to be able to integrate this DDP up, right? And so in order to integrate it up, I need to produce a DP value, which is actually the more correct speed there, right? I need to produce the actual, I need to produce the actual velocity. And since that wants to be smooth, I need to take the acceleration, and I need to produce the delta from that, right? So I need to say, look, I'm going to take however much I said I was supposed to change here, And I guess that's one of those two. Yeah, because this is all in 3 dimensions now, right? So I need to take however much I was supposed to do here. I need to integrate that up. So I need to produce this by multiplying by my dt, you know? And I need to add whatever the old one was. So whatever the camera's dp used to be. Yeah, I'm going to do that now. So once I produce those values, then finally I need to take the step. So whatever the p-value should have been here, I need to take that actual step. And doing that actually requires me to, if I wanted to, do the integration a little more carefully here. You know, technically p is equal to whatever the acceleration was here. And I should probably write the dt on the other side of this, right? It's actually 1/2 at squared, right? If I integrate it up twice. And that's the acceleration. That's actually the correct way that it would apply over the time step. And then I've got my velocity, which I've just computed, which is this, right? So that's that gets applied times the dt. In this case, I just want to apply the old one. And then I want to add whatever the old position was, right? So that's the full integration with the proportional derivative controller in it. And then I've got my my case where I would just set it directly equal to the target p without having to do anything else. And so in that case, again, this would just become 0, or actually it would become whatever the dp of the target was, because that's, I'm just moving along with it. And my ddp in this case would be completely 0, in case I cared. I don't, but in case I do, right? And so, yeah, looking at what's going to happen here, I still need an if to see whether I'm close enough to the target that I shouldn't actually take the step. And so this update here is one giant vector, right? This is effectively a new p, in a sense, right? And so if I wanted to take this as a delta p, it's just this, right? That's the amount that I'm moving it by. If I wanted to take that delta p, what I could do is say, look, if the length of the delta p is less than some amount I don't care about, and I could avoid the square root here by just saying, look, if the length squared is less than, you know, some epsilon, right? Or, sorry, if the length squared is less than the distance to the target, right? So in this case, whatever the total delta p was, and these are not necessary anymore. So if the length squared is less than how far I have to go, then just, you know, or maybe I'll do it the other way. If it's greater than, then do the actual update step. Otherwise, just assume I arrived at the target. You know what I mean? And then we just track that delta p each time. So, you know, when we write everything back, we write back our delta p as well, so our camera keeps its acceleration and stuff. And that's, again, just a very simple controller. They're not good. They can overshoot. They can do a lot of stupid things. But the bonus is, at least if I debug why it's doing something weird like that, if the length squared is of the delta p, sorry, it is less than. If the amount I would move it is less than the total, that's what I meant to do. Okay. And now you can kind of see, like, the camera's just kind of doing its thing. I gotta, again, we don't have a lerp for the for these guys right now, so we gotta kind of pretend they're, you know, out in La La Land there. Like so. But that will give an always smooth approach there. You can kind of see. And the easing in is not quite where we would like it. and so you can see it kind of circling there a little bit. And so, you gotta adjust these terms a bit to make them stiffer. I don't know what the best terms would be. Probably something higher here. I don't know. We could put those in as dialable parameters as well, right, in our camera code. Yeah, so I think we want some pretty high values for A there. So, again, most of the reason why you use one of these is just because proportional derivative controllers have the benefit of they kind of just work, and they don't give you any resolved, like any absolutes, so you can get some drifting and some weirdness in there, but they don't really have any other issues related to them in that sense. So I would like something better than that, but just that exploration did not seem fruitful. And it seemed like we were going to get something pretty hard to control, if that makes sense. We can clamp these values as well, so we can make sure that we're actually not going to get into some really bad state, because that's usually what you worry about when your values start to overflow. So we can put a clamp in there, and we should probably do that. But the other thing I want to do is, for these, with the target expected focus min z and that stuff, I think what I'd like to do there is just make it so that I'd like to have some notion of the interpolation being based on how far we are from the target, if that makes sense. Like, I want the expected min focus and stuff. I would like that to be kind of more based on just where the camera is. But the problem is it's hard to know how to do that exactly. I'm not sure how to put in a good blend here, something that would make these things track the distance better. I mean, we could kind of make them follow this approach. And another way maybe to do that would be to say, look, we can figure out how far we are from the target camera and use that as the blend amount, or make that imply the speed. I don't know. Blending these together is going to be sort of tricky, because if you think about what we actually want, excuse me, when we're setting these, like the entity focus and the room focus values here for these, blending those together, is going to be tough, because you can see what happens there, how we get a blackout, right? That's because they're getting set instantaneously to the new one. So we want to blend smoothly between the new one and the old one, but what we really want is something that maintains sort of a notion of of where the intermediate target would have been versus us. Like, I almost want to say that when you're doing this blend, if you look in here, the room focus Z is based on the camera arm. And the camera arm is something that we sort of vaguely know what it is, because we know what it was, and then we know what it's going to be. And so you could almost imagine interpolating that as like another target parameter that could be interpolated along with this, right? So yeah, I don't really know how else we would do that other than setting it up to interpolate sort of the same way that this is interpolating. Or just probing it. I don't got a lot of ideas there, if I'm honest about it. You know, that's the target entity focus Z. The current entity focus Z is just looking at where the, right, like, wherever the entity is that we're trying to look at, we know that wherever we are, so this is the actual entity focus Z. And so the thing that I'm wondering about is, like, do we want to just base things off of that more? I don't know what that would do. Probably nothing good. So yeah, a lot of puzzlers here. I'm not sure what the best way would be to make that code happen. Because you want it synchronized with something that I'm not sure exactly what it is. And you want it to interpolate at some rate that's roughly commensurate with how fast the camera is interpolating, but since the camera is using a proportional derivative controller, you really don't have that option. You know? So that's a little bit tricky. But I don't know. So I'll just throw them into the proportional derivative controller with the rest of the system and see what happens. I wish I had a better answer for you than that, but I don't. And so if we were to do that, you know, we'd just compute that directly, right? We would say, all right, you know, what's the speed of these things? Right? And then we'd update them. So we'd just say, yeah, like, this code literally, and this is all F32s now. But you're literally doing this. And when you go to compute this thing, you're going to use the same thing, but now like the targets and stuff are specified from here. So you'd basically have like, okay, whatever the target expected focus min z is, right, is where we're going to, and whatever the expected focus min z is where we're coming from. You don't have this term because you know it's always 0, because you don't have a changing value of that, really. Although I guess you could argue that you actually do when you're going downstairs. So maybe I shouldn't say that. So maybe you really do have this, which is the DP target value for this thing, right? And then you've got the velocity in there. You then compute what your DP is, and you do it exactly the same way. And you use the, you know, expected focus min there. You compute the delta with the exact same code. And then you see, you know, if If the absolute value of those two things, or just the square of those two things, you could do, right? You could also just do if square. Then you set, otherwise you don't, right? Since I don't really think this should be changing much, because most of the time the target relative to the camera, since you're moving the camera, I think you could probably eliminate this term. So I'm going to say, like, for now, this is always 0. And so you would do this for both of them, for both min and max. Right? Oops. And then you'd call it a day. So yeah, that's, I think, most of what you would be doing. And, you know, if we did this real quick, we could just say those are the 3 update steps. And we can pull that out into code that actually makes more sense, and is a little more used on the next stream. So the total delta P in this case I need to actually compute, right? So this would be this value. And in this case too, we've got the P value is not actually that, right? It's this. So in this case, we would just set them directly. And off we go. And you can see how we would be pretty easy to just make utilities that did these for us. So even though it looks like a lot of code, it's just the same code. So we should be able to just run that twice by calling a function, right? And we'd be done. So, you know, that in theory attaches the same proportional derivative controller to both things, but they're in different spaces, and one's 3D and one's 1D. So, you know, we don't have a lot of reason to believe that they're actually going to work particularly well. And you can kind of see that there. It's taking a lot longer to do that. Now, we can adjust all the parameters to try and make it so they, you know, are stiffer, or because, you know, they're, like I said, they're in different spaces. So I don't know. I mean, we can certainly say that, you know, the AB here are not the same AB that we have here. You know, maybe this is like way stronger or something. But like I said, that's maybe something for next stream, because I'm like massively over time now. It's like almost 4 o'clock. And you can see where the DP target might have been useful there, right? Because that would probably have improved the speed at which it would interpolate up to the entity there. Are we not using the entity? No, we are. So why was that? That also does seem... Yeah, well, anyway. Maybe I'll make this even stronger than it was. Because it just doesn't seem like it catches up quite quickly enough as it seems like it should. Oh, and you know why? It's because it's not actually measuring what the entity z. It's measuring what it will be after it interpolates. So I can sort of see why that would be wrong too. So we have some more work to do there, right? Yeah. So we'll have to take a look at that. I'll go to a really brief Q&A, but I gotta go. Like we're way over time here. This is a disaster. Paul MMH. Moving my Rocket to Linux is always like sort of an eventual goal someday, you know? We already have a problem where like I don't want to use Windows 10 because I really don't like Windows 10. It's very unpredictable and bad. I mean, they can't even ship updates anymore, right? You saw what happened with the October update. They tried 3 times to ship the update and couldn't do it. It's like a 4th time's a charm kind of situation. And it's just the unpredictability of it updating it on its own and doing all these ridiculous things. It's just not. Windows 10 is not a real operating. It's not a production quality operating system, right? Anymore. I mean, you're not. It's not something you would ever trust to run mission critical stuff. You know, it's so far past that. And so, you know, like, I would like to switch to Linux because I can lock that down. You know, I can pick which kernel gets built and I can put it on the machines, and I don't have to worry about Microsoft like ruining our week all the time by changing some update or doing whatever, right? And so, you know, I really want to do that, but the problem is that since most people don't use Linux for things like this, game development on Linux is not that common. Most of the stuff isn't there. I mean, I don't even know what the status of Nsight is on Linux. Hopefully it's, you know, okay. Or there's something like that there that you can use reliably, right? But the debuggers aren't very good. You know, GDB is very bad. It crashes most of the time on this machine. Like I just tried to debug a very simple like program. Wasn't nearly as complicated as Handmade Hero, and GDB would crash every second run. Just GDB. Let alone if I try to attach a front end to GDB, and that crashes on its own often, right? And so, like, it's just not, I don't know, like, the actual debugging of it seems pretty bad. The actual dev environment for it just seems really bad. And I don't know why, you know? I don't know why it's so bad, since it's something that lots of people do dev on now. But is the plan to change the character face direction when they move in a direction, or will that be mapped to a different key? It's mapped to a different key. So right now the way that it works is you can point any direction you want. And you can hop in any direction you want, which will probably remain the same. I don't know for sure, but probably, right? You can see the proportional driven controller stuff just doesn't work that good for that, for sliding. We may want to change it to something more linear, like just update those linearly. You know, like we may want to not have an AB value. Like you may want to just do this. And you just say, hey, yeah, we don't, you know, we don't use a proportional derivative controller for these. We just say, look, if we were going to step, you know, the delta, well, you know, I'm not going to do that right now. There's too much code there, right? If there were a truly good, better than Visual Studio debugger for Linux, would that make Linux viable for game dev? Probably, although I don't know how good the GPU support is still. It used to be very bad, so hopefully that's better, but I'm not really sure. I guess what I would say is it would be a big, big improvement. And you need both a debugger for code and for GPU. So both of those need to be available. It looks like the average sized room is currently too big to be seen without scrolling. Is that what we want in the end, or is it just the average sized room is still unstarted? Yeah, we will play with that later. But we want to support both. Oh, as for code releases won't be released till after the game. It says right on the webpage, 2 years after the game gets released, we will release the code. Did the updated speed get applied for the camera for the fog? All right, I'm going to wrap it up. I got to go. All right, thank you everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always, even if we couldn't quite figure out how to get a good solver-based approach in there. I don't love proportional derivative controllers for a lot of reasons, but if that seems to be the most straightforward way to get one that's tunable, then I guess that's what we gotta work with. People use them for a reason. I do some other things sometimes in my own code, but yeah, I can't think of anything in this particular situation that really is going to be simple enough. So I don't know. So we may just be stuck with that, and if we are, that's okay. Anyway, that's it for now. I'll be back probably next weekend with the final one before winter break. You can always check the watch page for the schedule. I try to keep it updated. Until then, have fun programming, and I will see you next time.